morning. My name is Isaiah. This is my partner Andrew, and we represent team on Semiconductor, SMPS. And our project is to design a software package that will help engineers design power supplies using on Semiconductor products. So what is an SMPS? SMPS stands for switch mode power supply. And in our case, it's just a small electronic chip that's about 7 millimeters by 7 millimeters, and it's a voltage regulator that will convert one voltage to either a higher or lower value. In our case, the switch mode power supply will be used in automotive applications and will be connected to the car battery. The motivation for our project was to make it easy to simulate a power supply. We want to improve the customer experience and discontinue using old software. So right here I have a screenshot of a MathCAD file, and this is currently how engineers design switch mode power supplies. As you can see, this is not a very user-friendly process, and in fact it's quite complex and difficult to use. Our best anticipated outcome is a modern software package that will be more efficient than conventional software. And here we have a table comparing what our project will accomplish versus what conventional software is capable of. We will include error checking, automatic component calculations, power efficiency and thermal dissipation calculations, as well as interactive graphs. By comparison, conventional software can either not incorporate these features, or the features are there, but you have to reload the software every time you change the inputs. To accomplish our best anticipated outcome, we will set limits on the customer inputs, suggest component values based on those inputs, calculate the power dissipation of both the chip and the external components, and we will graph the performance and stability of the power supply in terms of the gain and phase. And as you can see from this diagram, first the customer inputs have to pass validation before any of these other parameters can be calculated. If the customer inputs do not pass validation, then the customer has to enter in new inputs that are within the limits of validation. One of our key accomplishments was a demo program, such as shown here. I have a screenshot of this program that was used in MATLAB. And this is just graphing the curve of the current voltage relationship of a diode. Now this won't be used in the final product, but it does demonstrate a couple of key points. You'll notice that there's a lot of parameters that are being used here to calculate this curve. If you change any one of those parameters, the graph will update automatically. So that feature will be used in our final product. Another key accomplishment was becoming more familiar with switch mode power supply design. Prior to this year, our team had little experience with switch mode power supply design, so it was important for us to expand our understanding in this area. To do this, we followed the design methodology available in datasheets from On Semiconductor, and we performed many calculations by hand. Then we compared those calculations with Excel files that were available from On Semiconductor. And by doing this, we're well equipped to continue to next semester with a solid foundation in switch mode power supply design. Next, Andrew will talk about additional accomplishments of our project.
When beginning the design process, we started out by creating a flowchart which defined the intended functionalities of the user, as well as the simulation options that the users have, and the potential consequences of each choice. For example, in this slide, we show a snippet of the top part of our flowchart, which is related to the configuration file. In order to further capture the main thoughts from our flowchart, we created a top-level diagram which illustrated the workflow of the user. Furthermore, we created activity diagrams specifically for each part of the graphical user interface, or the GUI, to identify each of the possible use cases. For instance, we show a part of the activity diagram on the right side of the slide where the user can first select a value, have it be validated based on whether or not that value fits within the minimum and maximum parameters of that component, and then that value will be set. Additionally, we created class diagrams for each part of the graphical user interface, such as the one shown on the right, which is for our slider, so that we can understand how we will programmatically implement each part of our graphical user interface. This shows each of the functions, methods, and variables that we will use. Moreover, we use schematics from On Semiconductor for each of the buck converters, boost converters, and other power supplies that they would like to utilize. Within each of these schematics, we achieve the ability for the users to alter any of the values of each component. For example, vSelect, as indicated by number 15 on this specific schematic, can be altered. In addition, we created many functional and fundamental building blocks to our graphical user interface, such as the slider that is shown in the bottom left of the slide. Within this slider, you can alter the minimum and maximum parameters, and the user can change the value by using the text box. Going forward, the remaining challenges that our team has headed into the spring 2019 semester is to compose a part configuration file that can be read by our computing software of choice, validating inputs, creating and executing a test plan, exporting and printing data from our design development tool, and finalizing the documentation package for Semiconductor. Ultimately, we would like to thank all the people that have provided us with guidance during this process. Thank you.